Heat transfer and phase changes. Phases of matter transform between the three different phases due to changes in energy. The shift of the three phases is a physical change which occurs in a substance. We have solids, liquids, and gases which can interconvert between each other. If we look at an overall representation, there are 6 different terms that refer to changes within these systems. A solid can transform into a liquid through a process that's referred to as melting or fusion. It can transform to a gas directly through a process called sublimation. A liquid will transform to a solid through a process called freezing or solidification, and to a gas through a process referred to as evaporation or vaporization. A gas can transform directly to a solid through a process called deposition, and to a liquid through a process called condensation. Looking at liquids, we can understand the heat properties of a liquid by the overall process of evaporation. This gives us a fairly good indication of a lot of what goes on with liquids. Now, considering liquids are substances, just like any other, that has an average kinetic energy that are proportional to the temperature, despite the fact that the overall kinetic energy is average, specific particles within the liquid will have faster or slower overall velocity. So some particles have higher kinetic energy, some have lower. The particles that have high enough kinetic energy can actually escape from the liquid and transform into a gas phase. At the same time, particles of a gas, which have lower energy, can be captured by the liquid and returned to a liquid phase. The overall temperature of the gas and the liquid as a combination determines the ratio of the particles that are captured versus those that escape. If I have a situation where a liquid is exposed to an open container, those gas particles won't necessarily stay near the liquid. They'll wander off into the rest of the gas. And so overall, the process tends to favor the escape of a gas, and that's why if you let something like water stand for a fair period of time, several days, you can see the water level continually drop till it eventually disappears, as all the water winds up in gas form and wanders off to other places. Now, factors that influence evaporation are the overall intermolecular force of the substance. Things like water with high intermolecular force tend to evaporate at a much lower rate than something like acetone, which has a relatively low intermolecular force compared to water. Temperature also affects the rate of evaporation. The higher the temperature of the liquid, the higher the overall average kinetic energy, so the more particles are able to escape from the liquid more effectively. The surface area affects the rate of evaporation, and if you've ever taken something and spilled water, for instance, on a table, you'll find that it evaporates much more quickly than water contained within a cup, because there are more points at which that liquid is exposed to the vapor around it and enables those particles to escape at different locations. If I take a liquid and a vapor and I contain them within a sealed container, they'll establish what we call a dynamic equilibrium. This is a process in which we have equal rates in both directions, so the rate at which the liquid becomes gas and the gas becomes liquid is equal. Individual particles, however, will still continue to transform between phases. Something that is a liquid will go to become a gas, something that is a gas will become a liquid. Liquid vapor pressure reflects this dynamic equilibrium that we experience. When we have an equal shift between gas and liquid, a certain amount of gas is dependent upon the temperature at which the whole system is contained. So the dependency upon whether a substance is primarily liquid or primarily gas is a result of the average temperature that it is held under. The amount of vapor then, it depends on the given temperature, and the amount of vapor at any given temperature is referred to as vapor pressure, because this vapor that exists within the closed container exerts a certain pressure on that container. Factors that influence vapor pressure are the intermolecular force. The lower the intermolecular force overall, the higher the vapor pressure, because the more the substance will be able to get into the gas phase. Volatile liquids like gasoline then have higher vapor pressures than liquids that are not as volatile like water. The higher the temperature overall, the higher the pressure, because number one, the higher the average kinetic energy, the more particles can transition to the gas phase, and number two, the faster those particles will be moving, so the more pressure they'll be exerting. Raising temperature then causes the vapor pressure to increase. Boiling point is a point at which we have free conversion between liquid and gas. The vapor in a liquid causes bubbles to occur as they're heated, and they will rise towards the surface. If the vapor pressure is less than the atmospheric pressure surrounding the liquid, those bubbles will collapse and release the particles back into the liquid, causing them to be recaptured by the liquid. However, if the overall vapor pressure is high enough, those particles or those bubbles will reach the surface and explode, releasing the vapor into the atmosphere surrounding the liquid, and those vapor particles will then be free to move away. The boiling point occurs when the vapor pressure of a liquid is equal to the atmospheric pressure around it. So boiling point is dependent upon atmospheric pressure. Vapor pressure is temperature dependent. As temperature increases, vapor pressure also increases. Eventually, the vapor pressure will reach atmospheric pressure and the liquid will boil. Vapor pressure depends only on the temperature of the liquid. The boiling point depends on the atmospheric pressure. This is why things like pressure cookers are effective. If you put a higher overall atmospheric pressure on a substance, it requires a larger increase in temperature for the vapor pressure to reach the atmospheric pressure, and so you're going to be cooking something at a higher temperature, which causes it to cook faster. At the same time, if you try to boil water up on a mountaintop, where you have a lower pressure, that will cause the temperature to boil at lower overall boiling point, so your water will be cooler than you would if you were trying to cook at a lower altitude with higher overall atmospheric pressure. Different liquids have different vapor pressures, and the higher the vapor pressure of the liquid, the easier it is to boil. Something like water, which has a low vapor pressure, tends to boil at a much higher point than something like an alcohol, which has a much higher vapor pressure. If I heat the mixture of things, for instance, if I'm heating a mixture of alcohol and water, the thing which has the highest vapor pressure boils off first. This is a process of distillation, so if you've ever considered something like distilling spirits, like trying to make whiskey or things that have a higher alcohol to water ratio, the distillation process works because something like alcohol with a higher vapor pressure is able to boil off before water, which has a lower vapor pressure. So you're able to concentrate the one liquid more than you are the other. Looking at heat transfer in liquids then, in order to raise the temperature to boiling, we have to apply a specific amount of heat. The amount of heat that's needed to raise a liquid to boiling temperature depends upon the specific heat capacity of that liquid. Remember, specific heat capacity is measured in joules per gram degrees Celsius. If we add heat, the temperature will increase until a liquid reaches its boiling point. The term molar enthalpy of vaporization is a term that is used to express the amount of heat that's needed to be added to vaporize a mole of a substance at its boiling point. So after a substance reaches the molar heat of vaporization, if you've added enough heat to vaporize that substance, additional heat will then increase the temperature of the vapor. We can express the molar heat of vaporization in mass terms as well, just as we can in mole terms, so we can have it expressed in kilojoules per gram as well as kilojoules per mole. For example, the molar heat of vaporization of water is 40.7 kilojoules per mole, or 2.26 kilojoules per gram, at 100 degrees Celsius measured at 1 atmosphere pressure. The heat of condensation is the opposite of the heat of vaporization. It is the amount of energy needed to be given off rather than absorbed in order to condense a substance. So since it reverses the process, while evaporation is endothermic, having to take in energy, condensation is exothermic. So we reverse the sign on the heat of vaporization, and we get the negative delta H vap of the water, which would be negative 40.7 kilojoules per mole, or negative 2.26 kilojoules per gram. An example of this, if I want to know what mass of water can be heated at 100 degrees Celsius with 155 kilojoules of energy, I know that the delta H vap of water is 2.26 kilojoules per gram. So if I multiply 155 kilojoules by 1 gram per 2.26 kilojoules, I'll get 68.6 grams of water. In a similar problem, the amount of energy needed to boil a substance at 178 degree grams of water that start at 35.6 degrees Celsius first have to heat the water until it reaches the boiling point, and then I can condense it, or can evaporate it. So looking at the specific constants we need, the first step is to heat. We multiply the specific heat capacity by the mass and the change in temperature, and that gives us 47,960 joules, or 48 kilojoules. The second step is taking the amount of substance and boiling it. So the 2.26 kilojoules per gram times 178 grams gives us 402.3 kilojoules needed to boil the water. The total energy then is a combination of the two at 450 kilojoules. Solids also have similar heating properties to liquids. Just like liquids, we have a free phase of transition with solids. The temperature-free conversion to a liquid from a solid is referred to as its melting point. The melting point depends on the strength of the attractive forces in a substance, just like it does with a liquid. The temperature has to increase until the kinetic energy is high enough for the substance to separate. Pressure doesn't change the melting point very much. It does change boiling point quite a lot, as we've seen. The process at which a substance is able to convert to a liquid is referred to as the heat of fusion, which is measured also in kilojoules per mole. We can express it just like the heat of vaporization in kilojoules per gram. For water, for example, the heat of fusion is 6.02 kilojoules per mole, or 0.334 kilojoules per gram, at 0 degrees Celsius in 1 atmosphere. An example of this process, if I want to know what mass of water at 0 degrees Celsius can be melted with 186 kilojoules of energy, I look at the heat of fusion of water and multiply the 186 kilojoules of energy by 1 gram per 0.334 kilojoules, and I get 557 grams of water that can be melted with that energy. Another similar problem, what is the energy necessary to melt 206 grams of water initially at negative 6.12 degrees Celsius? Well, first I have to, just like with the boiling, heat the water. So the specific heat of ice, rather than liquid water, is 2.09 joules per gram degree Celsius. So I multiply 2.09 joules per gram degree Celsius by 206 grams of water, and then the temperature change, which gives us 2,635 joules of energy, or 2.64 kilojoules. The second step is to melt the substance. So we take 0.334 kilojoules per gram as the heat of fusion of water, multiply it by the mass of 206 grams, and we get 68.8 kilojoules. The total energy is a combination of both at 71.4 kilojoules of energy. Looking at a transformation from a substance below freezing to a substance above boiling, we can draw what we call a heating curve. A heating curve is a process we can follow from the change in temperature. A substance changes temperature only when it has completely gone through a phase shift. If I look at the heating curve below, for instance, I will increase temperature to the point that I begin to melt. Once I start melting, I have to continue at the same temperature until I've applied enough energy to completely melt the substance before I can continue to increase temperature. I have the same plateau again when I reach the boiling point. I have to completely convert from a liquid to a gas in order to then continue increasing temperature. So the first step is to heat to the melting point, after which the process has to go through melting. Once it's all melted, it can continue heating to the boiling point, and then it has to go through the process of boiling. Once it has all boiled off, the vapor can then be heated past the boiling point. Heating curves will then account for both the heat of vaporization and the heat of fusion.